Welcome to AI Paper Podcasts, where we dive into the latest AI research and break it down for you. Today, we're tackling a really big challenge in computer vision. How do you build AI models that can really see and understand the world, but without needing, endless streams of labeled data?
Yeah, it's a fundamental problem. If you can crack that, it opens up so much.
Exactly. And that brings us to today's paper, DINOv3 from Meta AI Research. It feels like a major step forward in self-supervised learning for vision.
It really is. They're aiming high, trying to create a kind of universal visual encoder that just works well across loads of different tasks and image types.
Okay, so that's our mission for this deep dive. But first, for everyone short on time, let's do a quick rundown the key takeaways from DINOv3. What should people know?
All right, first up, DINOv3 massively scales self-supervised learning, SSL in vision, like way beyond what we've seen before.
Second, the scale of the model itself is huge, a 7 billion parameter vision transformer. Think of it like a supersized AI brain for vision.
And it was trained on a massive but carefully chosen dataset, nearly 1.7 billion web images.
Okay, point 3.
This is the really clever bit. They introduced something called gram anchoring. It's a new technique specifically designed to fix a big problem. You see, with these huge models trained for a long time, the ability to see fine details, the dense features, it tended to degrade. Gram anchoring stops that.
So it keeps both the big picture and the tiny details sharp.
Exactly. Both global and local features stay strong.
And the final result.
The result is this incredibly versatile model. It's hitting state-of-the-art on a ton of stuff: segmentation, 3D understanding, object detection, even analyzing satellite images. And often it's beating models trained with lots of human labels, all with a frozen backbone. You just take the pre-trained model, plug it in, and it delivers great features.
Wow, okay, powerful global and local features right off the shelf. That's quite the summary.
Definitely sets the stage. So foundation models, they're really becoming central in computer vision now, aren't they?
They are. These big pre-trained generalist models offer this amazing ability to generalize. You train it once, and it can adapt to many different tasks. That's huge for practical applications.
And self-supervised learning, SSL, is what's really driving a lot of this excitement, particularly with DINOv3.
Right. Explain that a bit more. How does SSL work here?
Well, instead of needing explicit labels, the AI learns from the raw image data itself. It might, say, try to predict a missing patch of an image, or figure out how different augmented views of the same image relate to each other. It learns inherent patterns.
So it bypasses the need for expensive human labeling.
Exactly, which is why it's so powerful for domains where labels are scarce or impossible to get. Think medical imaging, histopathology, remote sensing, astronomy.
Yeah, you can just feed it massive amounts of unlabeled images.
Precisely. DINOv2, the predecessor, already showed how well this could work, giving really robust general-purpose features.
But scaling SSL up to the level of DINOv3 wasn't straightforward. They hit some roadblocks, right? What were the main challenges they were trying to solve?
There were 3 big ones. First, data collection. Just having billions of web images isn't enough. How do you pick the useful ones from all that noise at scale? Curation is critical.
Makes sense. Garbage in, garbage out, even with SSL. What was the second hurdle?
The optimization horizon. Basically, many common training schedules need you to know upfront exactly how long you'll train for. With these absolutely massive data sets, that's really hard to predict. You don't know the finish line.
You can't just use a simple cosine decay if you don't know the total steps.
Exactly. And the third one, this was maybe the most critical, especially for scaling beyond DINOv2, the degradation of dense features.
Oh, we touched on this. The fine-grained details.
Yeah. The model's ability to understand local details, like patch similarities, actually started getting worse after a certain point in long training runs, particularly for the really big models. Global understanding might improve, but local precision suffered.
It's a serious limitation if you need pixel-level accuracy for things like segmentation.
Absolutely. So fixing that was a major goal.
Okay, so those are the problems. What were their main objectives for DINOv3 then?
3 core things. 1, train a truly versatile foundation model for many tasks and domains. 2, specifically fix that dense feature degradation issue. And 3, release a whole family of models, different sizes, that people could actually use off the shelf.
Make it practical, not just a research curiosity.
Exactly. And they tackled this with some really neat innovations, starting with the data. LVD1689M, they call it.
The 1.7 billion image dataset.
Yeah.
How did they curate it? You said curation was key.
Right, so they started with this massive pool, like 17 billion public Instagram images, already pre-moderated, which helps. Then they used two main strategies. First, hierarchical k-means clustering. They used DINOv3's own features to cluster the images, and then sampled to create a balanced set of 1.689 billion images. This gives broad visual concept coverage.
So it sees a wide variety of things.
Yeah. And second, they did retrieval-based curation. They took existing high-quality data sets for specific tasks and found similar images in their giant pool. This makes the training data more relevant for downstream tasks.
Clever. Kind of boosting the signal for things they care about.
Pretty much. They also threw in some standard public data sets like ImageNet and Mapillary Raw just to round things out.
And how do they actually use this mix during training?
They use a mixed sampling strategy. About 10% of the time, they trained on just ImageNet 1K high-quality, clean data. The other 90% was batches mixing everything else together. They found this blend gave the best overall results.
Interesting. So data sorted. What about the model and training? You mentioned a 7 billion parameter model.
Yeah, VIT7B. A big jump from DINOv3's largest, which was around 1.1 billion. Architecturally, it's a custom vision transformer using axial ropey, rotary position embeddings.
Ropey helps with different image sizes and aspect ratios, right? Makes it more flexible.
Exactly, more robust to resolution changes. But what's really interesting is how they simplified the training optimization.
How so?
They basically ditched complex learning rate schedules. After a warm-up, they just used a constant learning rate, constant weight decay, constant teacher momentum for 1 million iterations.
1 million, wow. That simplifies things massively. No fiddling with decay steps.
Right. Much less hyperparameter tuning allows for more open-ended training. Big practical win. They combine standard SSL losses, Dino, IBIAT, Coleo.
And the scale of training must have been immense.
Oh yeah. Batch size of 4096 images across 296 GPUs. Using that multi-crop strategy, 2 global views, 8 local views per image. Standard stuff there, but at a huge scale.
Okay, but the real secret sauce seems to be this gram anchoring thing for the dense features. Let's unpack that. What exactly was going wrong?
So imagine the model's learning, classification accuracy is going up, things look good globally. But if you test its ability to do, say, semantic segmentation, that performance starts to drop after maybe 200,000 training steps.
Even as the overall model gets smarter.
Yeah, it's paradoxical. They visualized it by looking at patch similarities. Early on, if you picked a patch, the model could clearly show similar patches elsewhere in the image. Nice, clean similarity maps.
Okay.
But later in training, those maps became noisy, scattered. The model was losing its grasp on fine-grained, local consistency. The features were becoming less distinct at the patch level.
So how does gram anchoring fix this?
Okay, it's quite elegant. It doesn't directly mess with the patch features themselves. Instead, it looks at the structure of their similarities. It calculates the gram matrix, basically, a big table showing how similar every patch feature is to every other patch feature.
Capturing the pattern of similarities.
Exactly. Then it introduces a loss term that encourages the current model's gram matrix to look like the gram matrix from an earlier version of the model a gram teacher saved from when the dense features were still good.
Ah, so it's guiding the relationships between features, not the features directly.
Precisely. This lets the local features still adapt and learn, but keeps their relational structure consistent and sharp. It prevents that noisy degradation.
And they apply this later in training.
Yeah, that's key. It's a refinement step applied after the main million iterations. It specifically targets and repairs the degraded local consistency, even if it had already become noisy.
Like a targeted tune-up for fine details.
You got it. And they saw it worked. It improved the IBOT loss, suggesting synergy, but didn't really hurt the global Dino loss. So it was doing its job specifically on the dense features.
And the visual results.
Night and day, apparently. The paper shows visualizations where DINOv3's dense feature maps are much cleaner, much more precise than DINOv2 or other models. You can clearly see object boundaries or corresponding patches.
And those noisy similarity maps.
They become clean and coherent again after the gram anchoring refinement. Really convincing proof it's solving that core problem.
Okay, so the tech is cool. But how does DINOv3 actually perform on real tasks? Does all this innovation translate?
Hugely. The improved dense features mean it excels at tasks needing that fine-grained understanding, but it's still great at high-level recognition.
Give me some examples.
Okay, semantic segmentation, drawing pixel-perfect boundaries around objects. State-of-the-art results on standard benchmarks like 80/20K, cityscapes, VOC. Same for monocular depth estimation, predicting depth from a single image. Top results on NYU V2, KTTI.
And this is with the frozen backbone, right? Just training a small head on top.
Yep, that's the power. The core features are just that good. It consistently beats other SSL models and even weakly supervised ones in these dense tasks.
What about 3D?
Strong performance there, too. Good at matching key points across different views, which is vital for 3D reconstruction. It also boosts performance in unsupervised object discovery, finding objects without labels, because its feature maps are so clean.
Video tasks.
Yeah, it tracks objects well in videos due to temporal consistency. And it performs strongly on video classification benchmarks, too. The dense features help capture motion and action details, but it's not just about dense tasks. The generalization is also really impressive.
Meaning it works well on data it hasn't seen before, out of distribution.
Exactly. On tough ODE benchmarks like ImageNet-R, ImageNet-Sketch, ObjectNet datasets designed to trick models, DINOv3 shows massive gains over DINOv2, like 6 to 13% improvements.
That's substantial. How does it compare to other big models there?
It's basically the first SSL model to reach performance comparable to the top weakly supervised models, like SIGLIP2, on these hard ODE tasks. And it's the most robust to standard image corruptions, like noise or blur.
So it's tough, versatile. What about things like image retrieval? Finding similar images.
Erratically better than DINOv2 there as well, especially on challenging artistic or historical image datasets where fine details matter. Though models trained with text data still have an edge if the task relies heavily on reading text within the image, which DINOv3 doesn't explicitly do.
Makes sense. And the classic benchmarks. Object detection, segmentation.
New state-of-the-art for frozen backbone object detection on Kokio. Just train a small detector head and it gets top results. Shows really precise localization.
And segmentation.
Same story. State-of-the-art MIOU on 80/20K, Coco stuff, cityscapes, VOC. Again, just training a segmentation head like Mass2 Former on top of the frozen DINOv3 features. It really validates the quality of those dense features.
It seems like plugging DINOv3 into existing pipelines just gives an instant boost.
Pretty much. They showed combining it with depth. Anything V2 gives state-of-the-art depth estimation. Putting it into the VGGT pipeline improves camera pose estimation, multi-view stereo, consistent gains across the board for 3D tasks.
So it's not just one giant model, you mentioned a family.
Right. They released models from VT small all the way up to VT7B and beyond. And across the board, these DINOv3 variants significantly outperform their DINOv2 counterparts on dense tasks, often by large margin, while staying competitive on global tasks.
Giving users options based on their compute budget.
Exactly. And these models handle high-resolution inputs well, up to 4096 by 4096, and are stable across different resolutions at inference time, thanks to how they were trained.
What about making these huge models practical? Distillation.
Yes, they showed effective distillation. They could train smaller student models like VITH+, using the giant 7B model as a teacher, and the student achieved performance very close to the much larger teacher.
That's crucial for deployment. You get the benefit of the giant model's knowledge at a more manageable size.
Definitely. And one more thing, text alignment.
Can it understand text prompts? Like zero-shot classification?
Not inherently, as it's vision-only SSL. But they showed you can align it with a text encoder afterwards. By combining the global CLS token feature with pooled patch features, you can align both global and local visual understanding to text. This gives really good results on dense zero-shot tasks, like segmenting based on text descriptions.
Okay, that adds another layer of versatility. Now, you mentioned satellite imagery earlier. That seems like a totally different domain.
It is, and that's what's so impressive. They took the same DINOv3 SSL recipe and applied it to a massive data set of satellite images, almost 500 million of them.
Just trained at DINOv3 7B from scratch on satellite data.
Yep. And that model set new state-of-the-art results on geospatial tasks like estimating forest canopy height and dominated the GeoBench benchmark across segmentation, detection, and classification tasks.
Even compared to models specifically designed for satellite data.
Often, yes. Even though DINOv3 only used the standard RGB bands and a frozen backbone, it frequently outperformed specialized models that used more spectral bands or task-specific fine-tuning.
That really speaks to the power and generality of the SSL approach.
It does. Interestingly, the satellite-trained DINOv3 was best at metric tasks like height estimation, while the original web-trained DINOv3 was actually better at semantic geospatial tasks, likely due to the diversity of objects it saw during pre-training. Shows they have complementary strengths.
Incredible. Okay, let's try and wrap this up. DINOv3 feels like a landmark paper in self-supervised vision.
Absolutely. It's a huge leap, showcasing what happens when you successfully scale data, model size, and solve critical training bottlenecks like that dense feature degradation using innovations like gram anchoring.
And for the listeners, the engineers and researchers out there, what's the big takeaway?
It means we're getting closer to having truly powerful, general-purpose visual understanding models that don't need mountains of labels. These are becoming off-the-shelf tools, providing state-of-the-art features for a vast range of tasks, usable across different resource levels.
So a final thought to leave everyone with. We're seeing these incredibly versatile foundation models emerge, bridging standard vision tasks and expanding into domains like geospatial data. What does this suggest about the future?
Well, it makes you wonder, right, if one SSL approach, one frozen backbone, can be this effective across such diverse visual inputs, from web images to satellite data, how far can we push this? Could future models handle even more modalities, solve even more complex problems, perhaps without any domain-specific retraining?
What new science, what new applications open up when a single, powerful visual AI can understand contexts as different as a cat video and a shifting glacier, providing both the big picture and the fine details right out of the box?
It really does change how we might think about building and deploying AI vision systems, a fascinating direction.